Okay, so we're continuing to talk about probability, and I will remind you, a probability is an area of probability is an area of mathematics where one treatment of the subject is that it's made up of two things. There's a probability space. It's otherwise called a sample space or a formal statistical model that is a set of possible outcomes and the probability of any of these outcomes occurring. In addition, there's some extra rules, things like that disjoint events have probability 0 of occurring together because they're disjoint. That would be like flipping a heads and a tails on a single coin flip. These are disjoint. They are not independent. This function maps every outcome to some number between 0 and 1, but no negative numbers. And the sum of all of the events, the sum of all of these need to equal 1. So if you flip a coin, you can have a 0.5 chance for heads, 0.5 chance for tails. You cannot have a 0.5 chance for heads and a 0.4 chance for tails, because you're missing a 0.1% of something happening. So that would be an invalid function. And given these two things, a set of possible outcomes and a function that maps those sets to some probabilities, with these extra side notes, that is everything that you really need to know to start making calculations about probability and making statements about things that could be true, or making predictions and having them on a firm footing that that will work. So last class we started to talk about this thing called a conditional probability space, and this is a circumstance when from the original space that you have, omega, there is some subset of it, some subset of these events that you're being told has occurred. And so here you can sort of forget about everything else except for this subset. And this subset becomes your new world. So in this example of rolling a die, the whole world are 6 possible outcomes. And I could tell you that the die roll was an even number. Sorry, this is wrong. Make it an odd number. 1. Ah. So this is the original world, and the original world has 6 possible outcomes, each equally likely. So the 1 gets evenly spread out across 6 things, leaving a 1/6 probability for any individual event. But I could consider, what is the probability that the roll odd die? So let's That's not right at all. So I'm defining an event, and an event is a subset of the world. So here, this event is defined by these three things. You could get a 1 or a 3 or a 5. And each of those happen with probability 1/6. And so the probability of the single event is a half. That's an example of an event that I could tell you it happened. The die was odd. Given that the die is odd, what's the probability of rolling a 1? So let me write that here. Given an odd die roll, what's the probability of it being 1? I'll give you a minute to think about it. If you think you know, you can either unmute yourself or type in the chat. One-third. Excellent. Yes, Mateo, it is 1/3. Do you have a mic?
Yes.
Great. So why is this 1/3?
Because you're given that the die roll is odd, so there's only 3 possibilities, 1, 3, or 5. So each is a 1/3 probability.
Excellent. Great. Thank you. Yeah. Sorry, I just muted myself. So what Mateo said is that now that you're given this, there's a 1, a 3, and a 5. But now this is a new probability space. So here on the left was the white is the original probability space, but now we're in a new probability space. And so the probabilities here get re-weighted to be 1/3 each. And so now in this new probability space, we want to know what's the probability of getting a 1, which is this, 1/3. Okay, so that's all that a conditional probability space does. There is a shorter way of calculating it. Its definition. This is the probability of A and B divided by the probability of B. So here's the same calculation using this definition. So here, the probability of 3 and the die being odd is this, 1/6 in the original space. And then you divide it by the probability of it being odd, which is the green space. Okay? But intuitively, this is what's happening. You're given that something is true, and now you're asked about a probability, given that that's true, that something else is also true. So the given that this thing is true is itself a probability space. And it's within that now known probability space that you're calculating a new probability. So each of these probabilities, these blow up by 2. They were 1/6, but now they become 1/3 because the probability of this green thing is 1/2. So each of these blow up by 2 times, or by 1 over the probability of this, which is 1/2. Okay, so this part here in the bottom, the probability of B, you divide by it because this blows up the probability values in the original space appropriately. And then the probability of A and B is figuring out the amount of area that A takes up inside of B. It won't always be the case that these are the same things. Here, the probability of 3 and the probability of 3 and the die is odd happens to be 1/6. That doesn't have to be that way, though. Okay. We derived Bayes' theorem. Bayes' theorem is another way of thinking about conditional probability. So here, the definition of conditional probability, we just defined the probability of A and B divided by the probability of B. In Bayes' theorem, this part, the probability of A and B, gets replaced with the probability of B given A times the probability of A. And so we showed how to obtain this. You define 2 different probability functions. These just come from the definition of conditional probability. The second equation, you rearrange stuff just by algebra. Basically, you move the probability of A to the left-hand side, and then you have the probability of A times the probability of B given A, that this is equivalent to the probability of A and B. So this is the in words, the probability of A and B is the same as the probability of A happening times the probability of B happening, given that you know that A happened. So this is a very important equation that's used a lot, especially in sciences, where it's considered updating your beliefs, I guess. So the probability, if you think of A as being a hypothesis and B evidence for that hypothesis. So the probability of global warming given this evidence that we see. What is the probability of global warming given this set of evidence? You can calculate that by saying, what's the probability of this evidence given that global warming were true? So now I'm going to imagine a world where I know that global warming is true, and that has a certain probability. Like just by itself, without evidence, there could be the probability that global warming is true. Are there ever any exceptions to this theorem? No. This is, the proof. This is by definition of things in probability. We're also assuming algebra is true mathematics. And given those two things, this is true always. There are two philosophies. Well, there's many more than that, but there's two major ones in probability. One is called the frequentist interpretation. The other is called the Bayesian interpretation. And the Bayesian interpretation is something I'm kind of explaining now. It's based on this idea of Bayes' theorem. So, continuing this example of global warming and evidence, you could say that without evidence at all, one could argue on what the probability of global warming would be. So you have that probability. Now, given that you're imagining or you're assuming that global warming exists, then what would be the probability of this evidence that you see for it? And then you have to readjust your probabilities according to how probable the evidence is by itself. It rains on Tuesday. That would have a very big probability. So the probability of B conditioned on A, this isn't very strong evidence. So your probability of global warming, given that it rained on Tuesday, will probably be a small probability. This will be a small probability because the probability in the denominator is big. So having something big in the bottom will make the whole thing smaller. Right? If I have 1 over a tenth or 1 over 100th, this is equal to 10, this is equal to 100. Okay, so as the bottom gets smaller here, then the actual number itself gets bigger. Here, the probability of rain would be a very large probability, the probability of rain on Tuesday, which is going to push this number, the probability of global warming, given that it rains on Tuesday, to be a smaller number. Because the evidence itself isn't very strong. The probability of seeing it anytime is big. Therefore, the probability of trying to make a conclusion based on that evidence is something small. Okay? So this is the way that this applies to scientific thinking. And it's also used, you can use it for lots of things. Generating words, language models, they're called. If you wanted to have a machine write a book, you could use this to do that. Really nothing other than this one theorem that you make some assumptions about it being true, and anyway. Are there any questions about this derivation or the intuition behind what this theorem is saying? I really don't know what people's backgrounds are as far as derivations like this. This is a fairly straightforward one, but maybe it's the first time you're seeing something like it. I don't know. But that will help me calibrate how to address other derivations. Following so far. Okay. Great. Here, this was just an example to emphasize the probability spaces. given that a fair die roll is even, you cannot say that the probability of a 2 is 1/3. It's the probability of 2 given that the die is even is 1/3. And here the fair die, this tells you that there's 6 sides and that each one of them has a probability of 1/6. So if you read a fair die or a fair coin, that's just sort of an indication. It's a shorthand for both the set of outcomes and the function. Okay. Then we went through some more examples. I won't go through each of these again, unless you have a question about something in particular. Let's see. This was about flipping a coin 2 times, and then what the probability of a this is more of a joint probability. Right, so another way to intuitively think about the meaning of a conditional probability is it's the percentage of A that's inside of B. This is just another example of conditional probability. This I brought up before about a number on the bottom getting smaller, making the whole thing get bigger. This, we talked about a new definition of independence. So, independence has 2 different definitions. You can use either one of them. If you can use both, pick one. But depending on the information you have, you might prefer one over the other. So, just to remind you, independence. Definition 1 is the probability, A and B are independent if, and I'm underlining if because if this is not true, then A and B are not independent. So this isn't something that always works, but if it works, then these things are independent. That's the probability of A intersect B is equal to the probability of A times the probability of B. I don't know if you guys like this or not. And probability of A equals the probability of A times the probability of B. The second definition, A and B are independent, again, if the probability of A given B is equal to the probability of A. So somebody telling you that B is true doesn't change your belief about the probability of A being true. And up above here, this is just an example of that. So dependent events, that if today is Monday, tomorrow is Tuesday. This is not a independent event. We sort of show that explicitly by coming up with the probability space, which includes the set of possible outcomes, the probability function, and then using our definition. So what is the event A? What is the event B? Here, today is Monday, tomorrow is Tuesday. And then we see if these things are equal. So this is the definition of conditional probability. And we notice that these things are not equal. The probability of A given B is not equal to the probability of A. Therefore, by explicit proof, by explicit proof, we show that these are dependent events. Can we say the probability of die equals 1 equals 0, but not the probability of die 2 equals 1/3?
This was from, it was like in green writing, the question.
Yeah, let me see. Here?
Yeah. So I was just wondering why, like, because it's given that the fair die roll is even, so we can say that the probability of die equals 1 equals 0, but then we can't say that, like, where it says false, probability of die equals 2 equals 1/3. Like, isn't it just given either way?
Good question. Yeah. Actually, you cannot say any of these things. Oh. Right. All of these statements on the left are false. This is false. This is false. This is false.
Okay.
Actually, the probability die equals 1 is 1/6 because this is a fair die. But the probability that the die equals 1 given the die is even, this is equal to 0. So this is true, this is true. These are not true on the left, none of them.
Okay, thank you.
Yeah. Yeah, good question. All right. So that covers about everything with the theory of conditional probability, the math of conditional probability, and hopefully the intuition behind conditional probability, along with some examples of building probability spaces. I encourage you to try to come up with your own simple examples that you know are true, because they're simple, and even if you don't know the math behind them, you can just run with it because they're simple examples and you know that things work this way. And then to try to show that these things are in fact true using these simple math things that we're talking about: sets, probability functions, and simple equations. You can practice this with independence, with dependence, and with conditional probability. All of these are really the best way to learn. I mean, you could hear me talk for half an hour about it, but that's not worth 10 minutes of you yourself working through an example that that resonates with you. So I am going to end our discussion on conditional probability with a puzzle. So, a puzzle. Uh, okay. A knight wants to marry a princess. The princess is in one of 3 caves. In the other 2 caves, there is a dragon. Okay, so guy comes up. There's 3 caves. One of them is the princess, and in the other 2 are dragons. The princess could be in the first cave. She could be in the second cave. She could be in the third cave. That will eat the knight. If disturbed. Okay. So, question 1. What is the probability that the knight finds the princess? That's a question for you guys. One-third. Okay. Jelani, do you have a mic?
Yeah, I have my.
Okay, great. So you say the answer is 1/3. Okay. How do we prove that? Or why is it 1/3?
Well, of the 3 available options, if she's in one, if it's like 100% that he's gonna find her, if he does, he's gonna change. So I don't know if it's like one of those given answers, but there are 3 available options, and then 2 of them he dies, so that's less would be the
Can you try to think of a way to build a probability space for this?
Yes. Is everything?
So we have a set of outcomes.
Yeah.
Um,
The set of outcomes would be princess, die.
would be what?
Princess, die. I don't know what the dragon's gonna do. I'm assuming it's gonna die.
I'm sorry, I can't quite make it out. Your mic isn't super clear.
I was saying
Better.
princess, die. Because I'm assuming he dies with the dragon. I
Oh,
don't know.
princess, dragon?
Yeah.
Okay, and what's another possibility?
Another possibility is what would be the other possibility? Isn't that the set of all outcomes or whatever?
Well, do you know that the princess is in the first cave?
Oh, okay, I get what you're saying. I guess it would be PPD and then PDP. I didn't know that it was referenced to specific places um,
Oh.
on the page, but that makes sense.
Let's see. Okay, so one possible event is the princess is in the first cave. Another is that she's in the second, and another is that she's in the third.
Yes.
Okay. Let's. Okay. Let's try to do this. If these are possible events, then what would the probability of one of them be? Remember, the probability space is two things. It's the set and the function. So what's the probability of Princess Dragon Dragon?
It'll be 1/3.
Okay. To save space, I'll do this. Okay. So, does this probability space reflect this question?
No, I don't think so.
What's missing?
I'm not necessarily sure. Maybe because the added dimension of it, of like which page and season. I'm a little lost. I, I believe it could be like maybe like 1/9 is the actual probability. Um, but what the way I'm looking at it is you could choose, I guess, the first option, but you could be in the second. I'm not necessarily sure.
Okay, great. Yeah, no, this is a really, really good start. Thank you, Jelani. Does anybody else have an idea? We can build off of this. This is a start. So this is an example where we know what the answer is. Somehow you know that the answer is 1/3. So now we're just trying to show it formally. And there's a reason why we're showing this formally, because the next part, you won't know what the answer is. Probably. I don't know for sure. Okay, let me just pick someone out then. How about, yeah.
Yes.
Hey. So can you see something that this probability space is missing? Let me ask you a related question. Maybe this will help.
Okay.
This is the puzzle, right? How many, if you look at this sort of as a story, I guess, how many characters are there in this story?
There are 4 characters.
4. Which are the 4?
2 dragons,
Mhm.
princess, and a knight.
Perfect. Yeah, exactly. Great. So there's 4 characters to our story. And this probability space, how many characters is this using?
3.
3. Right. So this probability space, how would you describe what the probability space that we have right now, this one? What is this describing?
It describing about the princess, the princess in the first one of the cave.
Mm-hmm. Not just the first one in the cave. She could be in the second or the third.
Yeah.
So this is, I will say, probability the princess is actually in a given cave. So somehow we're like God now. We know where the princess and the dragons are in this scenario. So there's a probability that the princess is really in the first cave, or a probability that she's really in the second cave, or a probability that she's really in the third cave. That's what this is describing. It doesn't say anything about the knight or what the knight chooses.
Yeah.
Okay. So there's 2 ways we could go about this. We could make a big probability space that has all 4 characters together. We could also take this existing probability space that captures the princess and the dragons, define a second probability space that just talks about the knight and the choices he makes. And then using those 2 probability spaces, we could create a new big probability space that describes all 4 characters together. Yes, thank you, Jelani. Yeah, you're right. Which cave she's in. Yeah. So how about okay, yeah, we'll end on this. How about we'll do the longer thing, I guess. So I'll call this I don't know. Real cave. And yeah, how about you help me define the probability space? I'll call it Knight's Choice. Right, so now I'm just focusing on the knight, this one character. What would the probability space for the knight's choices look like?
he choose the first case and or choose the second cave or choose the third cave.
Great. Okay. And what is the probability function for that?
The probability of the first cave is equal to the second cave and equal to third cave equal to 1/3.
Great. Knight's choices. Thank you, yeah. All right.
Thank you.
So we have now two probability spaces. One that describes the possibility for where the princess and the dragons really are, and now another that describes the knight's choices. There's a few notational things here. Each of these have 3 events. Here, I'm putting these, each of the 3 events, I'm putting it in parentheses to emphasize that this is one event. Okay, this is the one event where the princess is in the first cave and the dragons are in the other 2. I guess I should put commas here. Okay, here I'm not putting the parentheses, although you could. If you wanted to, you could put it like this. That's fine as well. I just don't want people to get lost on the notation. Okay, I'll keep it like this just because I think it looks cleaner. Can you change the color? Sure. This blue color is no good. Yeah, let's... Here, I'll do a light blue. Okay, I want to keep both of these here. Right. So, now, I want to create a probability space of the real cave plus the knight's choice. Okay, so now this has all 4 of our characters together. How about Ishan? Do you have a mic?
Yeah, can you repeat the question, please?
Yeah. So we have here one probability space. Here. Here we have a second probability space. And now I want to combine them together to create one mega probability space. So, how do you create a new probability space from other probability spaces?
Would you combine the 2?
Yeah.
Like, would you... Yeah.
Yeah, how do you combine them?
You would put all of the events that could occur in one place and then put all of the functions for each event in another.
So first, let's just focus on the set, not the probabilities yet. Just the set.
Okay.
What would be an example element in this set?
Like, for example, if the princess is in the second cave, like, is that what you mean by event?
Okay, so the princess is actually in the second cave. So I'm assuming this one is true. Okay? And
Like another event that could happen?
well, this is not an event that can happen because this is leaving out the knight. Remember, we're combining these together.
Oh, right. So say he goes to the first cave.
Okay. Then he goes to the first cave. Right? So here the knight chooses poorly and he gets eaten by a dragon. This is one possible event. What's another possible event?
That the princess is in the first cave and he goes to the second
Great.
night.
And as you might imagine, there will be a number of these cases. A shorthand for this is this called cross multiplication or set multiplication. Does this ring a bell? Do you remember this? So you take the first space 1 and then you multiply it by the second space 2. And because these are sets, there's a way that you can multiply two sets together for what's also called a joint probability space. So this is a probability space jointly between space 1 and space 2. How about, and this will be my last question for you, Ishan, the size of this? How many different elements are there in this set?
I think 9.
Great. Yeah, 9. And this is 3 times 3, where this is the size of the real cave, and this is the size of the knight's choice. Excellent. All right. Thank you, Ishan. And we're going to take a break after this example, but I want to finish it just to give you something to maybe think about for a couple of minutes during the break. How about Royston?
Yeah, can you hear me?
Yeah. Great. So now we're still defining a probability space because this is not complete. We have a set, but we're missing the probability function. So what would this look like?
Yeah, would it be a combination of the like the choices that we have between like which cave he goes in and like which cave the princess is in?
Mm-hmm. Yeah. That's right. So what is...
Oh, so like what is the
Yeah.
probability of it?
Yeah.
Would it be
Mhm.
like I guess like DPD first cave, and then it would be like equal to 1/9. Like, you know, with all the examples, with all the possibilities, I mean.
Right. Yeah, so the probability of DPD in first cave. Yes, so you're correct with this. Equals 1/9. But this notation is not good. So the way to do this is you're actually... Here. Sorry, let me actually just rewrite this. Your intuition's right and everything. I'm just going to show how to write this formally so that you don't get confused, or at least just to show you how to do it. So Here, this probability function, I'm going to give it a subscript. So this is like, I'm trying to write something like this, where this A is a subscript of this. Apologies for my handwriting. So we want to know what the probability function is of this space. So that's why this is here. This, and let's say, for example, the probability of, what was the event that you said? I'm sorry, I forget. I erased it.
I think it was the DPD.
Okay.
And the first choice, and the knight picking the first cave.
All right. Great. First cave. Okay. So here's one event. Each event here, all 9 of them, need to have some mapping between themselves, and a number between 0 and 1. Doing this one. All right. Now this is equal to, you say, 2 different probabilities, each of which you know is 1/3, and that's how you're getting the 1/9 for that probability. What are the 2 probabilities you're multiplying? You're correct that the answer is 1/9.
One of them is the amount. I mean, the
Mhm.
like which cave he goes in.
Mhm.
So he goes in one of 3. Like he goes in the first cave, and then I'm still a little bit confused about the dragon princess dragon situation. So I'm not really sure. But I
Right.
guess it's one of 3 options. But I feel like he can't go. So say he goes into the first cave, and it just seems like is it the order that he's going in? But if he goes in the first one, then doesn't he die?
It depends. It depends on which cave the princess is actually in.
Okay.
Yeah. So here, first we'll just focus on one single event. Okay, so this is the event that the princess is actually in the second cave, and the knight chooses the first cave. Okay, that's what I've underlined in green. So just focusing on that one event. And this event is defined because we're combining 2 different spaces. The space with the real cave, without thinking about the knight, and the space that the knight is working from. So the number of different possibilities, there's 9 of them. Quickly, the princess could be in the first cave, and the knight could choose the first, the second, or the third cave. So those are 3 events. The princess could be actually in the second cave, and the knight could choose the first, the second, or the third cave. Or the princess could really be in the third cave, and the knight could choose the first, the second, or the third. And that's it. So those are the 9 possibilities. Taking just one of these possibilities, the princess is actually in the second cave, but the knight chooses the first cave. What's the probability of that one event here? And you can very quickly, when I talked about joint events, here, So creating a new space from other spaces. And so you had a number of elements equal to the number of elements from the first set times the number of elements from the second set. And you also had here, in this case of rolling 2 die, you would have 36 of these probability functions, one for each of the 36 possible outcomes. So here we have an outcome, a single outcome in a joint space that is built from 2 other spaces. And the probability, by definition, this is just the way it's defined to be, the probability of an event, of a joint event happening, is equal to the probability of the first event happening times the probability of the second event happening. You can think of them as being independent things. In fact, this is the definition of independence. The probability that the princess is in the first cave and that, this is the same as probability of A and B is equal to the probability of A times the probability of B. So actually, this is still just the definition of independence, because the knight is making a random choice. His choice of which cave to try is independent of where the princess actually is. So here, the probability of where the princess actually is, this comes from this first probability space. And so that's where the probability of 1/3 is coming from there. The probability that she's actually in the second cave. Separate than that, there's the probability that the knight chooses the first cave. And we have here that the probability that the knight chooses the first cave is also equal to 1/3. So that's where these things are coming from. Does that help at all?
Yeah, I get it.
Okay, so how many of these will there be for this probability function? This is one event that we've defined.
Yeah, would there be 9 options?
9, yeah. And 8 more. All equal to 1/9. Okay, great. Thank you. And yeah, thank you, Royston. And to wrap all this up before our break, I will choose, how about Emily?
Hello?
Hello. Okay.
Could you just repeat the question?
Sure. So what we're trying to do is, given this puzzle, there's a question that what's the probability that the knight finds the princess? And the answer is 1/3. That's the right answer. Somehow people just know it, but there's a lot going on in their head and stuff, and we're just trying to make it, we're trying to find this 1/3 using the math of probability. It looks kind of messy, but if you think about it, hopefully it makes a little bit more sense. But right now, we are trying to figure out how to get this 1/3 from this question. What is the probability that the knight finds the princess? In order to do that, we need a probability space to work in. That's this one here that's on the screen. Let me see if I can Yeah. So here we have a set of events, and here we have the probabilities of each of these events. 9 events, each with a probability of 1/9. So my question for you is, from this space, so that is, what is it? Oh, real cave and knight's choice. From this space, what is the event that the knight finds the princess? We can call it E. Do you remember what an event means in probability? An event is a subset of all of the different possible events. So, for example, if I have a die with numbers 1 through 6, I could define the event even as being 2, 4, 6, with the corresponding probabilities. So here, this is an event where each of these is coming from this world of a die. Okay, so that's how you define an event. From all of the possible outcomes, here's 2 of the possible 9. The event that the knight finds the princess. You lost? It's okay if you are, it's fine. Or are you thinking, or? I'll tell you, it will be a set with stuff inside of it. No, I cannot. Sure, yeah. Define, give me, yeah, give me like one possible event here, such as P first cave. Yeah, okay, sure. So P first cave, that means that P dragon. You're saying that the princess is actually in the first cave? Yeah, okay, and then which cave does the knight choose? First cave, great. First cave. Can you give me just one more event that works for this? So here, DPD third cave. Hold on. DPD third cave. Does the knight find the princess in this case? 2. Yes, great. Yeah, he would get eaten. All right. And how about the last one? Excellent. Great. Yes, DDP third cave. So, in order to answer this question, I know that this looks like a lot. You could have just jumped into building this by itself. I think that this is a good review for having joint probability spaces. You could just write this if you want, this thing. And you don't need to write any of this if you want, because this is a shorthand, it's true. If you just, you could just write this, and, the probability of this equals the first one equals the last one with dots in between, like we did here. That's fine. But because this is a class, it's maybe helpful to go through everything in great detail the first time. So, these are the 3 outcomes. And here... Here... the probability of E is equal to the probability of this first one plus the probability of the second one plus the probability of this third one. And each of these are 1/9. And that is where we get our 1/3. White instead of black. Yeah, I can make my board white instead of black. I'll do that after the break. If I do it, because unfortunately, because I'm using lighter colors, I need to go back and change colors and stuff, especially when I've been writing with white and stuff. Yeah, the next time I start a new page for something, when we get to expectation, and I'll start with the white thing. Okay. So, yeah, that's it. I should note that technically, when I'm saying probability here, it's the probability from this world, from this joint world. That's where each of these probabilities are coming from. I'm not writing those here just because it's already messy enough, and I don't want to make it messier. But formally, each of these probability functions are being applied to events from this joint probability space, which is why each of these are defined and they're equal to 1/9. So that is it. I will zoom back on this a little bit, I guess, to try to have people see it a little bit more. I'm not sure if that makes things worse because people are already having trouble reading it. But again, hopefully you have your own notes. That's the best thing. So I will leave this here. Let's take, let's say, a 15-minute break because it's been like an hour and a half. And I will see you all after the break.